off we go. So we're going to do the sorted edges algorithm on this right here. Sorted edges is what we use when we're trying to make a Hamiltonian circuit. Hamiltonian circuit is when we want to get to every single vertex. And in this case, we want to optimize that Hamiltonian circuit by finding the cheapest one, because there's going to be more than one circuit in a graph like this. A couple things to notice about the table with the weights for this graph. It is symmetric, so this is bidirectional, so we can either look at the upper part or the lower part. They both provide the same information, and lately I like to look at the upper part. And we can use just the table to do this, but I'm going to draw a picture of it to kind of back up what I see in the table. So first I'm going to redraw a graph, A, B, C, D, E, and F, and I'm going to fill in what the sorted edges tells me to do. What does the sorted edges tell me to do? Sorted edges has basically three conditions. One, grab the cheapest possible edge whenever possible. Two, if grabbing that edge leads to a premature circuit, then you can't grab that edge. Or if grabbing that edge gives you a vertex of degree 3, you can't grab that edge either. So those are the rules. So can't have a premature circuit, and we can't have degree 3 on any vertex. Otherwise, we grab the cheapest edge. So what do we got? On my version, I have a 1 from A to C. So I'm going to draw that 1 in here and label it. And then the next cheapest edge I see is from A to F. That's a 2. So I'm going to draw my A to F in, label it with a 2. Next cheapest one for me looks like the 4. And I'm going to circle it and hope it's going to work. That's going to go from B to C. And I'm good. So far, I haven't made a premature circuit, and I have not made a degree 3 vertex. All right, on a roll. 7 is the next single digit, it looks like, for me. And that would be from A to B. And A to B makes a premature circuit, so I cannot choose that. And it makes a degree 3, yeah, so that violates both conditions. So get rid of that. And I'm just going to cross out the 7 there, can't use it. Double digits, it looks like 10 is my next hopeful candidate, and that would be from B to E. And B to E, that looks legal, so that is a 10. Following that, let's see, in the teens, I have a 18 and a 19, it looks like. I'm not seeing anything else. So the 18 is from D to F. And let's go through this way. D to F looks legal. That is an 18. And looking at the graph, I can see I'm almost done. I need, let's see, no, I guess I am done. I just need D to E, and then I have a connected graph. So let's just double check that. I'm going to use a slightly different color to make sure I'm right there. So D to E. Looks like the only connection I need, and DE is a 59. All right, yep. And then I'm just going to go through with my highlighter and make sure that seems like a proper path, a proper circuit. So starting with A, I'm going to C, B, E, D, F, and back to A. And it is a Hamiltonian circuit because I hit each vertex exactly once each. And according to the sorted edges algorithm, it should be an optimized circuit, meaning it has the lowest cost of any other possible circuit. If we wanted to analyze all possible circuits, we could do the repeated nearest neighbor algorithm. But I think this is pretty good. So I'm asked to state my answer starting with A. And so there's 2 ways to answer that depending on the direction that you go around. So I'm going to answer it the way I wrote here when I did my check. I went from A to C to B to E to D, F, and then back to A. So that would be my answer here for the sorted edges algorithm, optimal Hamiltonian circuit.